All right, so in chapter 2, we start talking about independence, which we've talked about before. We talked about that back in chapter 3. We talked about if events were independent or dependent. And if they're independent, one event does not affect the other. So if we toss a coin and we roll a die, that's like tossing a coin and rolling a die are not going to interact with each other. One doesn't affect the other. But if a medical researcher wanted to know if there was a relationship between caffeine consumption and a heart attack risk, those wouldn't necessarily be independent of each other. So what they would do is they would organize data into a contingency table. So a contingency table is just a fancy way to show frequencies, observed frequencies. So we've got an R by C, R being rows, C being columns, contingency table. The observed frequencies are arranged into rows and columns, R for rows, C for columns. And then the intersection of a row and column is called a cell. So down here at the bottom, we have a 2 by 5 contingency table. We have 2 rows, male and female. We have 5 ways to eat ice cream, cup, cone, sundae, sandwich, or other, and how many people picked each one based on gender. So if we wanted to know the number of males that picked a sundae for their favorite way to eat ice cream, we would go to that cell, which would tell us 204 people surveyed were male and picked a sundae. So if we have 2 variables and we can assume they're independent, we could use a contingency table to find expected frequencies for each cell. So in order to find the expected frequencies in a contingency table, you're going to multiply the sum of row R times the sum of row C, the sum of column C divided by the sample size. So whatever cell you're in, you're going to take the sum from that row and the sum from that column and multiply them together and divide it by the total sample size. That's going to give you your expected frequency. So it feels a little weird when you're just saying that out loud, but once you start actually multiplying and dividing, it's not so bad. It's pretty straightforward. When you find the sum of each row and column in a contingency table, you're calculating the marginal frequencies. A marginal frequency is just the frequency that the entire category of one of the variable occurs. So regardless, like if we go back to the ice cream, regardless of if it was male or female, if we had 1,002 people pick a cup as their favorite way to eat ice cream. So that would be a marginal frequency, the total number of people who picked ice cream in a cup. The observed frequencies in the interior of a contingency table are called joint frequencies. So in number 1, a marketing consultant for a travel agency wants to determine whether a certain travel concerns are related to travel purposes. The contingency table shows the results of a random sample of 300 people. Assume that the variables travel concern and travel purpose are independent. Find the expected frequency for each cell. Well, in order to do that, we have to find our totals. So I'm going to just add another row and another column for my totals. So hotel room is going to be a total of 74. Leg room on a plane, 162. Rental car size, 28. And then other, 36. So that's the totals for my columns. Now I'm going to total my rows. So for business, 36, 108, 14, and 22 give me 180. 38, 54, 14, and 14 give me 120. Now, this final total here should add up to your sample size, and it should be the same for the total column and the total row. So 180 plus 120 is 300, but 74 plus 162 plus 28 plus 36 is also 300. So it should work out both ways. If it doesn't, one of your totals is wrong. So when we find our expected frequency for each cell, so the business hotel room cell is 36. So in order to find our expected value for that, that would be E11, row 1, column 1. We're going to take the total of that row, which is 74, multiply it by the total of that, the total of the column was 74. The total of the row was 180. So we're going to multiply those together, and we're going to divide it by our sample size. So 74 times 180 is 13,320. We divide that by 300. We have an expected value of 44.4. And we just continue on with that same process. So row 1, column 2 would be legroom on the plane for business. So 180 times 162. So that row times that column total divided by 300 is going to give me 97.2. I go to cell row 1, column 3 for rental car size in business. 180 times 28 divided by 300 is going to give me 16.8. And then my other column, so row 1, column 4, 180 times 36 divided by 300. $21.6. And then I go to row 2. So row 2, column 1, we got a row total of 120, column total of 74 divided by 300 is 29.6. Row 2, column 2, 120 times 162 divided by 300, is 64.8. Row 2, column 3, 120 times 28 divided by 300 is 11.2. And row 2, column 4, 120 times 36 divided by 300 gives me an expected value of 14.4. So those are all of our expected values for each of those cells. And we would use those to find independence test, basically another hypothesis test. But that would be your step 1. Now, when you're doing these all together, you don't necessarily have to show all the multiplication for every single one of these cells. I mean, you could if you wanted to, but if you were to just do it in your calculator and make a column for it or put it in that same cell as what your observed was, that's fine. That's totally your decision. How you decide to work that out is not a big deal to me. So after you find your expected frequencies, you can test whether the variables are independent with a chi-square independence test. So we're still using the chi-square table on page A19. It's used to test the independence of two variables. So using that test, you can determine whether the occurrence of one variable affects the probability of the occurrence of another. So you've got two conditions. Observed frequencies must be obtained from a random sample. Expected frequencies have to be at least 5. So it's the exact same conditions that we had in section 1. Those have not changed. Again, it's going to be real rare that those conditions aren't met. Okay, 99% of the time those conditions are going to be met. So when those conditions are met, the sampling distribution for the test is approximated by a chi-squared distribution with a degree of freedom of r minus 1 times c minus 1. So it's your number of rows minus 1 times your number of columns minus 1 every time. Your test statistic is the exact same thing as it was in section 1. The sum of our observed values minus our expected values squared divided by our expected values. So that's not going to change. We're going to do the exact same thing that we did before. So when we start an independence test, your hypotheses are going to be some variation of HO being that your variables are independent, HA being that they're dependent. So you're not going to want to say the variables, you're going to want to say what they are, whether that's, concerns of travel and reasons for travel or something completely different. When you're performing your independence test, you're going to verify your values came from a random sample. Your expected frequencies are at least 5. You're going to identify your claim and hypotheses, your level of significance, find your degree of freedom, critical value, rejection regions, find your test statistic, reject or fail to reject, and interpret in context of the original claim. So again, exact same thing as it was in section 1, exact same thing that we're doing back in chapters 7 and 8. Okay, so number 2, we're still looking at the marketing consultant for a travel agency. The same values, same expected values, so those are already in the problem for you. The ones in the parentheses are your expected. The other is what was observed. Our totals are already there. So the only thing we're adding on is that they're asking at alpha equals 0.01. Can the consultant conclude that the variables travel concern and travel purpose are related? So when we start working this out, our HO is going to be that travel concern and travel purpose are independent, and HO is just going to be the opposite. Travel concern and travel purpose are dependent. And they're asking if they're related. So if they're related, they're going to be dependent or not independent. So HA is going to be our claim. So we have 2 rows because we don't include our totals or our headings. So we have 2 rows and we have 4 columns. So our degree of freedom, 2 minus 1 times 4 minus 1, or 1 times 3, which is 3. So if we go to our chi-square table on page A19, and we go over to 0.01 and down to 3, we're going to have a critical value of 11.345. And again, all right-tailed tests here. So our rejection region is going to be greater than 11.345. So I'm going to kind of create my own little mini table down here with our observed minus our expected, and then that squared, and then that divided by our expected, rather than try to figure out a way to add it onto our table. So it doesn't matter what order you go in, because it's going to be the same either way. So you can go up and down the columns, or you can go across the rows. That really makes zero difference at all. So 36 minus 44.4 is negative 8.4. And I'm going to go ahead and just square it and divide by my expected values all at the same time. So if I square that, I get 70.56. And if I divide that by my expected value of 44.4, I get, remember, if it's not a decimal that ends, at least 3 decimal places when you round. So 1.589. Then I'm going to go on. So 108 minus 97.2 is 10.8. When I square that, I get 116.64. And when I divide that by 97.2, I get 1.2. 14 minus 16.8 is negative 2.8. Squared is 7.84. Divided by 16.8 is 0.467. 22 minus 21.6 is 0.4. Squared is 0.16. Divided by 21.6 is 0.007. And then I move on to my next row. 38.29.6 is 8.4. Squared is 70.56. Divided by 29.6 is 2.384. And then 54 minus 64.8 is negative 10.8. Squared is 116.64. Divided by 64.8 is 1.8. 14 minus 11.2 is 2.8. Squared is 7.84. And when we divide by 11.2, we get 0.7. And then the last one, 14 minus 14.4 is negative 0.4. Squared is 0.16. Divided by 14.4 is 0.011. So we're going to total that last column up, which gives us 8.158. So that's what we're comparing to our rejection region. So 8.158 is not greater than 11.345. So we're going to fail to reject HO. So we don't have enough evidence to support claim that travel concern and travel purpose are related. All right, so we're doing the same thing in number 3. If you feel confident enough in it, pause the video, try to do the independence test on your own, and then compare what you got on your own to mine. So a researcher wants to determine whether age is related to whether or not tax credit would influence an adult to purchase a hybrid vehicle. A random sample of 1,250 adults is selected, and the results are in the table. At alpha equals 0.01, is there enough evidence to conclude age is related to response? So HO would be that age is an independent response. HA would be that age is dependent in response. There's other ways you could word that. You could say age and response are independent, age and response are dependent or not independent. That doesn't really matter how you word it, as long as it means basically the same thing. They are asking us if there's enough evidence to conclude that age is related to your response. So that's going to make our claim HA. So I've got 2 rows and 3 columns here. So my degree of freedom is going to end up being 2. So when I look that up on my table, I go over to 0.01 and down to 2. I have a critical value of 9.210, which means my rejection region is going to be greater than 9.210. So since I didn't make this table very big, I'm not going to try to squeeze my expected values into that table. I'm just going to start a new table to make it a little bit easier. So I'm just going to move my values that I already had in this table over into my observed values. And then I'm going to find my expected values. So I'm going to start with row 1, column 1, and I'm going to go across the rows. So 589 times 475 divided by 1250 gives me 223.82. 589 times 450 divided by 1250 gives me 212.04. And then 325 times 589 divided by 1250 gives me 153.14. And now I'm going to start with my second row. So 661 times 475 divided by 1250 is 251.18. 661 times 450 divided by 1250 is 237.96. And then the last one, 661 times 325 divided by 1250 is 171.86. So observed minus my expected, and I'm just going to go ahead and every time I subtract, I'm going to go ahead and square it and then divide it by the expected, and just finish off each of those at a time. So 257 minus 223.82 is 33.18. Squared is 1100.9124. Divided by 223.82 is 4.919. And again, if it doesn't end, the decimal doesn't end at least 3 decimals when you round. And then the next one, 189 minus 212.04 is negative 23.04. Squared is 530.8416. Divided by 212.04 is 2.503. 143 minus 153.14 is negative 10.14. Squared is 102.8196. Divided by 153.14 gives me 0.671. 218 minus 251.18 is negative 33.18. Squared is 1100.9124. Divided by 251.18 is 4.383. 261 minus 237.96 is 23.04. Squared is 530.8416. Divided by 237.96 is 2.231. And 182 minus 171.86 is 10.14. Squared is 102.8196. Divided by 171.86 is 0.598. So when we add that last column, you should get 15.305. So that's going to be our test statistic and what we compare to that rejection region. So 15.305 is greater than 9.210. So we're going to reject HO, which means we have enough evidence to support the claim that age is related to response. Okay, so that is the end of this section. Hopefully it wasn't too bad for you, because it's very much like section 1. I'll post your homework on the assignment for this video, and also probably on the class stream, but it's page 542, 2 through 22 even. If you need help with anything, get a hold of me, email me, text me, get on Google Meet with me, whatever you need, just let me know.